Hi, welcome to VC Video 12.3 Part 2, more on velocity and acceleration vectors. But you'll see what I mean in the next example. So here's R of t equals a quarter t cubed plus 1I plus tj. We're doing it at the point 3, 2. Remember that's when x equals 3 and y equals 2. So here's me finding out that when x is 3 and y equals 2, that means that t equals 2. You simply set 3 equal to a quarter t cubed plus 1 and solve. You'll get t equals 2. I guess you could check and make sure, but of course that makes the other one work as well. So this is a set of parametric equations. Y is equal to t, so I can replace that t by y in the first equation. And I could then isolate y because they are asking you to graph it by hand. So what you have is, since you know that y equals x cubed looks like this, you know that x equals y cubed looks like that. And all this does, it moves it to the right one. And then it makes it, the steepness is affected, not that you would really notice. And then you would check for direction. So the graph looks like this right here, okay, this green graph right here. So the position vector at t equals 2, because they wanted it at the point 3, 2, which is at when t is equal to 2. So here is your 0.32. Here is your r of 2. And then when you take the derivative of this r of 2 is 3 halves. Where's my initial function? Right here. My v of t, of course, is going to be 3/4 t squared for my x component plus 0. And my derivative of this one is 1. So that's where I get the 3/4 t squared 1. And then from here, I can find v of 2, replacing that t by 2. So that gives me v of 2 is equal to 3, 1. So from this terminal point at the end of this r of 2, you're going to go 3 to the right and up 1. I know it's very hard to see that. So if you go 3 to the right and up 1 from the point 32, you'll be at the point 63. The acceleration vector you'll get from here, that's going to be 3 halves t comma 0. So when you replace t by 2, you'll get 3 comma 0. So from, again, that same terminal point, that 0.32 on the curve that they talked about, which is the terminal point of r of 2, you're going to go 3 to the right, but you will not go up or down. So that'll place you at the point 62 is the terminal point of that. Okay. Right, so one of the things you want to notice, and this would be a situation where if I drew a circle, this is what would happen, is that when the velocity and acceleration vectors are positioned with their initial points on the terminal point of the position vector in standard position, then the velocity vector, as you can see, is tangent to the curve at that point. If I go back, you can see that this blue vector is tangent to my green curve here at that point. Of course, here, it's tangent to the curve at that point because, of course, this is a line. It has the same slope the whole time. The other thing you'll notice is that if it's a kind of a closed figure and there is an interior of the figure, the acceleration vector will point into the interior of the curve. So that's just an observation. 23 to 28, use the given acceleration function to find the velocity and position vectors and then find the position at the time t2. Basically, what this is differential equations, okay? So, in other words, and I'm going to type that in right now for you. In other words, these are differential equations with initial conditions. So this is stuff that you've seen many times before, because of course a of t is actually the second derivative of the position function. So you're being given the second derivative, and then you're given these two initial conditions, because notice this is v of 0, not v of t, and r of 0. So you're told the velocity when t equals 0 is equal to 0 comma 4, and the velocity, the position when t equals 0 is the 0 vector 0, 0. Now it is a bit complicated here because we're dealing with this third dimension that we're really not supposed to deal with. So I'm going to pretend, I'm just going to get rid of the k right here, forget that. And of course there are no j's in here, which means it's 0j. So my acceleration vector actually is the vector 2 comma 0. And then these words right here, this expression right here, v of 0 equals 4j, that's an initial condition. If v of 0 is 4j, then in component form that's 0, 4. And if r of 0 is 0, then that means it's the vector 0, 0. So since they gave us this acceleration vector, in effect, the acceleration is the derivative of the velocity. So I'm going to go from the acceleration vector, I'm going to integrate it to get it to the velocity vector, and then I'm going to integrate the velocity vector to get to the position vector. So the velocity, the derivative of the velocity vector is this 2I plus 0j. I am going to integrate because I'm going to get rid of the derivative. So I'm going to integrate. Remember, you leave the I and the j on the outside. So I'm integrating 2 dt. And over here, I'm integrating 0 dt. So here, when I integrate 2 dt, I get 2t plus c1 because it's a different c than the other c and the I on the outside. This is 0t plus c2 and the j on the outside. But they told us the initial condition was that v of 0 equals the vector 0, 4. So I'm supposed to get the vector 0, 4 when I replace these t's over here by zeros. And then what happens, of course, is since these are equivalent vectors, the x coordinates would have to equal one another. So 0 would have to equal 0 plus c1, which means c1 is 0. And then the y component coefficients would have to be the same. 4 would have to equal 0 plus c2, so c2 is 4. So I now know that my velocity vector is this, and I'm replacing my c2 by 4, and I'm replacing my c1 by 0. So the velocity vector turns out to be the vector 2t4. Now the velocity vector is actually the derivative of the position vector, so that's 2ti plus 4j. And now I'm going to integrate to get from the derivative of the position function to the position function itself. So I'm going to integrate 2t dt, I'm going to integrate 4 dt, I'm going to get t squared plus c3, and here I'm going to get 4t plus c4, and then I'm going to use the initial condition. They said that r of 0 is 0, 0. So when I replace t by 0 on the right, I'm supposed to get the vector 0i plus 0j. Set the x components equal to each other, set the y components equal to each other. Aren't you lucky that they both end up being 0? So if you forget to put these c's, you'll luckily get the correct multiple choice answer, but I will have to ding you for free response. So now that we know that c3 and c4 are both 0, I can just take this equation here and replace those two constants by 0. I will get this expression right here, which of course is the vector t squared 4t. And they wanted r of 2, so I just replaced the t's by 4. Now, the position, I want to go back up here and look at these instructions again. Find the position at time t equals 2. When they talk about the position, they mean the actual xy point, not the vector. So the position of the vector value function, because it's where it is. It's a particle traveling along the curve, and it's exactly which point it is at. Okay, so here's just another example of the exact same thing. Here they're giving you the acceleration vector, which is the second derivative, and they're giving you two initial conditions. So very similar situation here. It's just a different function. Again, I'm ignoring the k's. And so I integrate the acceleration to get to the velocity, and then I plug in v of 0 is 2 comma 3. So 2, 3, replace the t's by 0, e to the 0 is 1. You'll find out that c1 is 1 and c2 is 3, so you can rewrite this line here, replacing c1 by 1 and c2 by 3. But of course the velocity is the derivative of the position function, so I can just integrate both sides to get to the position function. So now I'm integrating these integrands. I'll get e to the t plus t here, 3t there. Of course, I still have these constants. Again, I use the initial condition. It said that r of 0 was 0. So again, then you find your two values of c, and you finally have your position vector, and then you replace the t's by 2.